in all the early part because it'd be easier for me. Sorry, John. Take everything. You don't understand that. Okay. ברוכים הבאים ליום העיון לכבוד יום ההולדת 85 של אהרון יאיר. קודם כל אני שמח לראות פה אנשים שלא ראיתי 30 שנה, משהו כזה, זה כבר הייתה סיבה טובה לעשות את זה. אני רוצה דבר ראשון להודות לאפרת מורין שארגנה את זה יחד איתי, אבל בעצם אמרה לי, אתה יודע שאהרון בן 85 השנה. וזה היה ככה הפתעה, כי אנחנו כולם רגילים לראות שהאיש צעיר, אני לא יודע אם אתם יודעים, אבל לפני שבוע הוא פרסם עוד מאמר, ובשדה הוא עדיין מסתובב, עדיין דוגם, ועדיין עובד, אבל לנו, חלק מתלמידיו והקולגות שלו, שלאורך השנים, אני הכנתי 4 עמודים, אני מוותר עליהם, אני מדבר בשביל. אהרון, לי אישית הוא היה אחד אולי משלושת המנטורים שעיצבו אותי, וגרמו לי ללכת ולעשות מה שאני עושה. אהרון עצמו יש לו היסטוריה מאוד מעניינת, לא יודע כמה אתם יודעים. אהרון נולד בטבריה, וכדי להבין כמה הוא טבריאני ודובר מקומי, אני אזכיר את הטיול בירדן, שבו ב-95 אנחנו יושבים בוואדי בארנון במוצא שם, ויש שם כל אלה שמקרק בוקקים כדי לשתות את הערק שלהם למטה, ואהרון ניגש לדבר איתם, אמירם כמובן הולך איתו, אבל מי שמדבר זה אהרון, ואחרי 5 דקות הם שואלים אותו, אתה מסוריה? כי הערבית שלו הייתה כל כך טובה, אז זה מהמקום, אבל שם גילו אותו די מהר, ושלחו אותו בגיל 15 עם מזוודה קטנה, ללמוד בבית ספר שהיה אז בית ספר אליאנס, אני חושב, ואחרי זה הפך לבית ספר יהודי של פריז, ומורהו, מנהלו בבית הספר היה לוינס, שגרם לו ללכת ללמוד בסורבון, ואז הוא חזר לארץ ועשה דוקטורט פה, הצטרף לסגל באוניברסיטה העברית, ומאז, אז גם הצרפתית שלו, הערבית שלו, האנגלית שלו, פעם הוא כותב, קורא וכותב לעומק, הלוואי עליי, כי כשאני הייתי צריך לכתוב באנגלית או לתרגם משהו מצרפתית, הייתי הולך אליו, כי לכתוב לא ידעתי, באף אחת מהשפות וכולל עברית. ואהרון תפס אותי בשנה א' שלי, הייתי הטכנאי שלו, ומאז הוא פתח לי את כל הדלתות, עזר לי בכל דבר, ואישית, אני אישית חייב בעצם את כל הקריירה שלי, שזה עד היום, חברות וקולגיאליות, שעושים את אני מדבר חברות, זה הרבה שנים של ארוחות ערב ודאגה ומה קורה וכולי, ועם השנים הוא גם פתח לי פה ושם דלתות גם בחו"ל וגם באנשים שהוא הביא לארץ. אז זה ברמה האישית. ברמה העניינית, כולם צריכים לזכור שאם היום יש לנו, מי שמכיר את המערכת האמריקאית היום, יש את ה-Critical Zone Observer, את CZ, Critical Zone Observer, CV, שהיום זה אולי בארצות הברית אחד הדברים שמרכזים הכי הרבה מדע בקטע שמחבר את כדור הארץ המוצק לאטמוספירה דרך בליה, צומח, גשם, שטיפה, גיל של דברים. אז אהרון בעצם בנה פה בארץ ב-1972 בכספים ללא NSF'ים וללא החלטות בינלאומיות של ארגונים, הוא בנה כזה מקום שבו בעצם עובדים, מקום לכולם. סטודנטים שעבדו כמו חנוך שעבדו על תהליכי גשם נגר וחלק מסדימנט, אנשים שהצטרפו כמו איפה ששחת פה, שם למעלה שהצטרפו מהחלק האקולוגי ותרמו אותו, ובעצם זה חלק מהדברים שאנשים, יש פה אנשים ואני הייתי טכנאי שם, שם למדתי לעבוד, הם לימדו אותי. והאנשים האלה, כל אחד בתחומו, בעצם הם בנו משהו שהיום עושים את זה בלי לזכור שהיו אנשים שחשבו על זה כבר לפני 1972, אני לא יודע, זה היה הראשון, ואחרי זה נבנה עוד אחד בניצנה. הדבר הזה הפיק המון אינסייט להמון המון אנשים פה, על תהליכי גשם ונגר, ועל תהליכים של סדימנטים, ועל ההשפעה של איך אזורים משנים את תכונותיהם, אתה משאיר את כל הגשם אותו דבר, את כל האקלים אותו דבר, ובעצם זה שאתה מלביש את כל הנגב בלס, איך אתה משנה לגמרי את כל התהליכים ששותים. ואהרון היה חלק נכבד בזה, הוביל את זה, והוא עדיין ממשיך. כשרציתי להחליט מי אני מזמין אורח מחו"ל, because we're getting to the time, I moved to English, but I was considering who I should invite to give a talk from overseas, which the budget was small, but we decided to bring one person. And the idea was that if you think about it, what Tom Dunne did in Kenya and then in Vermont, and wrote a paper that all Aaron students had to read, even they didn't know English. That we broke down. Each sentence is Dunne and Blake 1970. Was the first paper I read in English. And the influence of Tom on us and their interaction during the years was always in the background. Tom was visited before, I think twice before. And he was not working really in desert most of the life, of this semi-desert of Kenya, 200 millimeter, you know, it's not a desert. And so I made the decision to invite Tom. He immediately responded that he's coming, and I asked him to give the keynote. So now, after he took, thank you to Aaron for a long career, and you can see who came here after to this building after, I don't know, some people I see faces weren't here for 20, 30 years. And I knew that people will respond to that, but now I move to the first talk. I allow Aaron to say thank you only in the end. In the end, he always wanted to say thank you. Yes. אתה לא יכול בלי זה. אתה לא יכול בלי זה.
הערה של גיאוגרף.
כן.
אהרון הוא לא טבריאני שפתי.
הוא התחיל, הוא נולד בטבריה.
אבל הוא שפתי.
אני יודע, אבל הוא נולד בטבריה. יש לנו עוד מישהו פה שהוא מטבריה.
בחלק הצפוני של צפת.
בחלק הצפוני של צפת, כן. אבל הוא מטבריה. And our guest speaker of today, Professor Thomas Dunne, he is now, for the last 22 years, he's in Santa Barbara. Before that, he was professor and chair at the University of Washington of the Geosciences. Originally, he is from Cambridge, and then Johns Hopkins for PhD. And he was a student of Red Wallman, who also visited here many, many times. And I have a list of honorary things of Tom Dunne. I'm not going to read all of them, but he won last year the Houghton Medal of the American Geophysical Union. He received the Distinguished Career Award of Geological Society of America Quaternary in Geomorphology in 2014. He's a fellow of the British Society of Geomorphology. He received the Gilbert Award of the American Geophysical Union and the Earth and Planetary Science Processes Group. David Linton Award of the British Society of Geomorphology, honorary member of the Japanese Geomorphological Union, Easterwood Distinguished Career Award of the GSA, fellow of the California Academy of Science, fellow of the American Academy of Science of Arts and Sciences, member of the US National Academy of Science, fellow long ago, and the list is going on and on. And now I ask Tom to deliver this. One more thing, Tom, one more thing. Because a few people here, I forgot that, a few people here that may remember this photograph. I don't know how many you recognize it. Hanoch, Aaron, Kiki, me. זה יצחק קיימת, דוב גביש. This is when real field experiment, full hill, when Aaron decided to do something, he took a full hill and put rainfall on it. It was, for me, 2 weeks to build it up, and for me it was like, okay, if you want something, just go and do it. And sorry, because Tom did the same thing, not in Amazon, but in Kenya, but now we move to, who will take care of you? And after the rescue.
Well, thank you very much for the introduction and for the invitation to be here. When Yehuda sent me an email, I was truly excited at the prospect of reconnecting with Aaron and honoring him with this celebration. I do something that I don't usually do, which is I told my students, I'm going to cancel the class for an entire week. I'll make it up to you with a field trip, but I'm going because I really want to participate in this. I want to see Aaron again, but there's also so many other people that I remember from previous times, either here or in the United States, where I've been affected by the literature of people. Even yesterday in my talk about my African work and trying to develop a new theory of water erosion, I was quoting data from Yאיר and Klein 1973, because I first met Aaron in 1978 in Paris, right? And that's where we connected with it, because we both had this idea that an important way of understanding landscape was to actually go out and observe processes as they happen in the field, and the small-scale, fine-scale evidence for how they work. And then taking that mechanistic understanding of landscape processes and then looking at the entire landscape and trying to understand how things change, not just that they do change, not just it changed from here to there, but what are the mechanisms by which the landscape works? And so that's the bond between us for going on 40 years, is that devotion to doing field studies where you monitor processes and interpret evidence for how things work. So I was really happy to be here to participate in this. But yesterday, my talk was, in a way, more about that kind of work that both of us have done, because I was talking about the activity of 5 millimeter deep flows of water over the surface of the landscape. And for this talk, you would ask me to talk about the Amazon, which is where I spent more of the last few years to even decades studying. So now I'm talking about flows that are 50 meters deep, not 5 millimeters deep. So it's going to be quite a switch. So I've been interested in how the Amazon transports its sediment from the Andes to the Atlantic Ocean. And I've worked on trying to on different timescales, what is the sediment budget over 10 million years, for example, since the latest uplift pulse of the Andes about 10 million years ago, the building of the Amazon fan. In that 10 million years, where did the sediment go? How much it went? But I'm going to pass over that scale. Talk a little bit about the work that we did on the sediment budget of the main Amazon itself, and then move to the tributaries, talk about modern concerns, modern environmental concerns. So I hope, I keep my eye on the time here. I think we're already later than I was expecting, so I might have to just jump over some of those things so I end on time. Anyway, Amazon Basin. Here, I think everybody understands the physiography of it, and the scale. It's about 5 to 7 million square kilometers, depending on where you claim is the the end of it, but it's formed, the Amazon River basin essentially was formed by tectonism. Right? It's not cut, not eroded by the Amazon River. The basin was constructed tectonically between a graben that fixes the mouth, two cratons, and the Andes that enclose it. Now, fortunately, it's geologically quite simple for that reason. And the most important thing for us to know for now is that all of the sediment, essentially all the sediment that the Amazon carries, comes from the 10% of the basin, which is the Andes. And the rates of erosion here are vanishingly small. Those of you who work in denudation units at 10, well, not denudation units, but sediment fields, they're about 10 tons per square kilometer per year of sediment. So this is where the action is. Now, structurally, it's a little bit more complicated than that because as the river is flowing down through this trough between the two cratons and the Andes, it crosses a set of transverse structures that go back to the Mesozoic and were thought to be dormant, but the river seems to be sensing very small changes along them, so that affects these arches, as the Brazilian geologists call them, are actually somewhat important to the story of how the river works in the modern era as well. Just to give you the first sense we got, these are cross-section of these arches, and here's these vertical lines. This is a cartoon where they cross the river valley. And the first sense we had that there was something related to tectonism was in the first, we never had a gradient for the Amazon. It's just too big to survey. But sometime in the 70s, the first space shuttle that NASA put up had a radar on it, and we were able to get elevations of the water surface of the Amazon at a few places, and from the water surface elevation, estimate gradients. And the interesting thing was, we found that these bars, which are gradients of reaches, we found that the gradient would increase slightly, then suddenly drop, increase again, drop, increase, drop, increase, drop. And I mean, I didn't know why that occurred. I was a bit mystified by it, but fortunately I found a Brazilian geologist at a cocktail party, and I sketched that graph on a cocktail napkin, and he said, oh, well, you know, this is the Jutaí arch, and that's the Gurupá arch, and this is the Purus arch, and so on, and there's a big tilting fault block here, and that's the reason that your gradients are like that. So it was the first clue that this river that I thought was like ultimate peneplain, alluvial heaven is actually a tectonically constrained large river with very slight, very subtle changes in gradient along it. And also, you know, what was also clear is that these were related to widths of the alluvial plain, and that the river essentially, in some places, bumps into the side of this trench that's in, and in other places is free to move backwards and forwards. And so, if you look, again, at old-fashioned technology, but these are old radar pictures from 1970, and they still, like, to my eye, they're still more revealing than even the modern Landsat images. But you can see that the outline here, the white outlines are the edges of the modern floodplain. And so if we're between arches, the river is free to have these very large meanders scale appropriately to the discharge of a river that's like that. And again, if you, those of you who like numbers, you can think that the peak floods in the Amazon at the mouth are like 250 to 290,000 cubic meters per second. Okay? And up here, they're probably half of that. So 150 cubic meters per second is the flood peak. So anyway, a river that big, left to its own devices, will scale river meanders that are you know that, I'm not sure if you can read this, but that's 20 kilometers. Okay? So we have amplitudes of 20, 30 kilometers there where the river is free. Whereas when it's going across one of these arches, the river is in a narrower trench in a way, just a few tens of meters deep, but nevertheless it's a trench, and it bumps up against the side, and the floodplain is much simpler and much narrower. And then again, further down, it's free to do all this movement that gives us a tremendous amount of complexity in the floodplain. So in the 80s and 90s, I'll quickly go over how we constructed a sediment budget for the main floodplain. We ran a set of cruises over this 2,500 or so kilometer reach between the Peruvian border here at a place called São Paulo de Alcântara, and all the way down to Obidos, which is at tide water. Now, we're still hundreds of kilometers from open ocean, so this is the head of the tides at Obidos. And at these places, we broke the river, the whole 2,000, slightly more than 2,000 kilometers, the whole reach up into 10 reaches, so averaging about 200 kilometers per reach. And we would measure the discharge and the sediment flux in and out of each of those 200 kilometer long reaches, and also the flow and the sediment coming in from all the major tributaries. And so, but on the other hand, I was working at that time with a guy from the Geological Survey, US Geological Survey, Bob Mead, and initially we had a US Geological Survey kind of viewpoint, which is gauging stations and what's going past the gauging station. But when you're on a river like the Amazon, it takes 6 weeks to do one of these campaigns. You spend an awful lot of time just staring at the side, you know, it's going slowly up the river, and you're just kind of watching. And it became obvious to my eye that there's a lot more activity than just what's the total amount of sediment going down in the channel. There's a lot of exchanges of sediment between the channel and the floodplain. And so I put together for 200 kilometer reaches this conceptual model of the sediment budget of a reach, and the exchanges of sediment between the channel and the floodplain. So again, to run through very quickly, the sediment budget for a reach would be, I've got suspended and bed load coming in and going out. I've got sediment coming in from tributaries. I've got sediment coming in from back erosions. All those red arrows are inputs. On the other hand, I've got sediment going out by diffuse overnight flow into channels and then out the bottom end. And so, you know, again, just conceptually, that led me to say, okay, well, this is the sediment budget for a reach. Each of these terms is one of those terms I just had an arrow for, tributary inputs and bank erosion and so on. So that led me to say, okay, well, maybe that's the target. I should quantify that budget. And so, and do it, by the way, for different grain sizes, because obviously on the bed of the channel there's sand and no silt and clay. In the floodplain, there's a lot of silt and clay. And the dominant component of the suspended load is silt and clay. So I've got to do this by grain size as well. So, you know, I did that. I'm very quickly point to the sorts of techniques that we had to combine to do this. This is our original technologies. The U.S. Geological Survey side of my head in a way. We had a 20-meter long boat, cruised up and down the river in it, 80 kilogram weight on, and a current meter, and collapsible bag suspended sediment samples, so we could run it down and up at a constant rate and get a vertically integrated sediment concentration for the entire depth, or we could put it down to particular depths and take a point sample with it and so on. And like I said, the original plan, which was conceived of by this guy from the Geological Survey, that was all we were going to do. But you know, we did that, and that was fine. But we also then my then graduate student at the time, started to try to quantify these other sediment exchange processes, like bank erosion, deposition on bars, and we did that by simply overlaying maps through time, navigation maps, and then eventually satellite images and so on. And we measured the amounts, the volumes, and the bulk densities by sampling, and the grain size composition of how much was coming in from the banks, and how much was going out on being deposited on bars. We, through a combination of field sampling concentrations and hydrologic modeling, we computed how much water was going over bank by this what I call diffuse overbank flow, how much was going out into the floodplain from these channels that lead water off from the main channel out into the floodplain. I think that was all, well, just to show you, we started to be able to use satellite technology. Leo Mertes was the person who first illustrated the use of multispectral Landsat imagery for measuring the suspended sediment concentration of the river. And so here you see for a reach of river, this is a low flow, this is a high flow. Basically, the warmer the color, the higher the sediment concentration. And you see things like as the water goes out into this channel and goes down the river, down this channel and back into the river, that at low flow, there's very little sediment in the water. We've got this greenish blue color. But at high flow, we get higher concentration water coming in, and then as it settles out, the colors get cooler because the suspended sediment concentration got lower. So using a combination of field sampling, taking a boat out, measuring what was going past there, and measuring what was going past there, and doing the same thing in the rivers and so on. We combine a lot of different types of techniques: direct field measurements, sampling, hydrologic modeling, how much water is going over bank into each of these channels, and remote sensing. So that's how we were able to put together these sediment budgets for 10 of these 200 long kilometer reaches. So this is, I'm not going to go through the details of it. Here's the entire 2,000 plus kilometer long reach. This is a budget for each of the reaches, and the different colors are these different exchange processes. The blue one here is bank erosion, and the red one is deposition in channels, and so on. And one of the interesting things that came out of that was you see that there are distinctive patterns here. This is iron, just as an example, just take the blue one. I don't mind what it is, but it's really bank erosion. You see that where the river is free to move around between those arches, then we have a lot of bank exchange, a lot of bank erosion, and a lot of deposition on bars, a lot of export over bank. Where the river is going through one of these arches and is constrained, then that sediment budget is also constrained. There's far less exchange. So again, that is interesting phenomenon where the very old tectonic structure of the continent is constraining the behavior of this big river in various ways along it, so that its modern behavior of exchanging sediment with its floodplain and creating a lot of floodplain complexity, that's all being constrained by these old structures, which was something that at the time really surprised me. We could do the same thing. This is, the silt and clay. I'm working with biologists on these trips. I have to call it fine-grained sediment and coarse-grained sediment, but to us, it's the fine grain is the silt and clay, and the coarse grain is the sand. So to do these budgets for these different grain sizes as well. Now, at the time I kind of left that for a while, but I've since been recruited to get interested in this again because geochronologists are starting to use isotopic techniques to date the sediment that's on the bed of the river. Only the sand. So their interpretation initially was that this represents all the sediment. It's just the sediment that they can sample and use their techniques on, like their cesium-137 and so on. But as a result, what they found out is that these are dates since a mineral was released, was broken up essentially by weathering, using this uranium-thorium disequilibrium technique, which some of you might use. And you get an idea of the birth of the sediment, if you like, when it was released by weathering from the bedrock and converted to regolith. And it gets down down the steep slopes of the Andes in just a few hundred years, and then moves down this one particular river, the Madeira, towards the Amazon, and it takes 17,000 years. So there's a time scale there for this transport. And they started asking me, well, what's controlling this? How is that sort of thing happening? And if we do the same thing down the main stem of the Amazon, what should we be looking for, and how should we interpret these numbers? So it led me to think a little more broadly about this, about what is the role of these exchange processes between channel and floodplain in storing sediment for a long time, during which time material get processed. I mean, the materials, after all, are not just sediment, it's not just sand grains, but the sediment has on it, for example, carbon. Some of the sediment grains are feldspars, and the feldspars weather. The carbon gets oxidized, and so on. And so this is just an example of the maturation of the sediment as you go from Peru, in this case, down to tidewater, to the Atlantic. This is one of Paul Potter's students, Franzinelli thesis. And so again, we have to remember that when this sediment is moving down the river, if it really does take a long time to go down the river, then what happens to it? What happens to the radionuclides that are in the sediment that are being interpreted by the geochronologists as reflecting something happening in the Andes? So as a result, I've gone back and started to say, well, look, if I utilize some of the work I did with one of my former PhD students, who actually got his field experience, interned with Aaron back in the 1990s. His name is Daniel Malmon. We did some stochastic modeling of sediment fluxes moving down through floodplains and river channels. And we came up with this idea that if you have some kind of alteration process, whether it's radionuclide decay or chemical decay, you can think of that alteration process as having a half-life. Not maybe the best measure for all these chemical processes, but the half-life is a common sort of easy to understand method. And if we take the ratio between the half-life of the alteration process and the average residence time of sediment in a reservoir, let's say a reach of floodplain, then we have that is going to control the degree of alteration of the material as it goes through the system. And it doesn't matter, these are typical sort of half-lives of processes. It's easy to understand in the case of carbon-14 or cesium-137, 10 beryllium. I got a scale from a weathering study that had been done that maybe feldspar hydrolysis in the floodplain sediments has a half-life of maybe 5,000 to 10,000 years. I'm still searching for organic geochemistry to try to put some numbers on these materials, but I haven't found the right person who likes to take a chance and give you a number. But anyway, as a result of that, then, and this sediment budget and Daniel's thesis, we, at that time, what we did is we put together a stochastic theory of how particles will move down, being exchanged. So imagine this is one of our reaches. Sediment comes in from Peru, then there's a chance that it will go out through the channel, or another chance that it will go over the floodplain. If it stays in the floodplain, there's a chance that it will be eroded back into the river by bank erosion. So all these exchange processes that I had quantified mechanistically for the Amazon can be turned into transition probabilities and used to model, in a statistical sense, the residence time of sediment. If it stays in the channel and it's in the bed, it's moving along the bed, how long will it take before it gets out? If it goes over the bank, gets into the floodplain, how long will it be in the floodplain before it gets recruited back to the channel by bank erosion, and so on. And so that's what I've been doing the last few months, and this is a bad visual, obviously, but I just wanted to give you a rough sense that these are the average residence times of sand and silt clay in the floodplain and in the channel. And these are each of my reaches, and you know, if I just, for now, I add them all up. So this, how long will it take a particle on average to get all the way out from Peru to the
years.
Years. So the answer is, if it stays in the channel, it takes about 300 years. If it gets into the floodplain, it takes most of the Holocene. Okay? Now, I've done the full modeling so that these are just the averages. If you calculate the distribution of probability, the whole probability distribution for each of these reaches, then some sediment gets into the floodplain and it stays for a much longer time. So the modeling allows me to say, okay, what fraction, if this is the average, 8,000 years, what fraction of the total sediment will stay there for 10,000 years, 12,000, 15,000 years, so on. To the point, and I'm now going this way, that last result of transition, the probability distribution, my wife and I completed after dinner last night at 11 p.m. So I haven't processed all this data yet. So now my task is to go back to these geochemists and say, okay, well look, this is my mechanistically based, from the original measurements, based understanding, turned into probabilities and modeled for long periods of time, and I've got the distributions, and now let me talk to you about your geochronology and what it all means. I haven't fully come to terms, I haven't fully processed the meaning of all these numbers I've now got for this question of the processing of carbon, radionuclides, feldspar, and so on, as the sediment moves along the river valley. But obviously, it's a real eye-opener about, I've got a scale now for about how long it takes. So I also can do this, by the way, just because one of my other former grad students, Rob Alco, and I, we did some of these field campaigns down two of the major tributaries, the Beni River and the Mamoré River in Bolivia. They're major tributaries coming out of the Andes and crossing the fallen basin of the Andes. So there's the fallen basin, here's the forebulge, and then they go that way and they join the major tributary of the Amazon, it's called Madeira. And this is actually the river down which the first data I showed you, the uranium thorium disequilibrium dates that were obtained for. So I'm now able to go back and, as a result of Rolf's thesis work, where again we've got these channel floodplain sediment exchanges over several hundred kilometers across the fallen basin. Again, I won't go into details of it because I haven't processed this yet, but I'm going to start doing this transition probability analysis for the fallen basin. And so that kind of gets me to thinking now about the sediment exchanges in the tributaries, not the main stem of the Amazon. And there's some interesting geomorphological implications and also some interesting environmental implications of this. Because again, if you look at these rivers, look at them both on the ground, or at least from the river, because again, you study a big river, you have a lot of time. You go down this river, it takes us about 3 or 4 weeks. So you get to, at night, you're just camping on the riverbank, and you get to spend a lot of time just overcoming your boredom looking at the river, right? So one of the things that you see, whether you do it that way or you look at satellite images, you get the impression on different tributaries of the Amazon that if the tributary is connected to the Andes, then there's a lot of evidence in the field that says, you know, this river is very active. There's lots of signs that it's moving around a lot. There's bars in the river. There's a lot of activity in the floodplain. There's many lakes in the floodplain. You really get a sense that having a large sediment source translates into strong spatial activity of the river. Here's, again, satellite images of it. This is what I mean by a lot of action in the floodplain. If you look carefully here, the color scheme, the pinkish are bars that have grown. The blue is sediment-rich water. So we've got a lot of activity here on the Beni because it's connected to the Andes. If we look further out into the basin, and the Purus is in the center of the Amazon, and the center of the basin, of the Amazon basin, but it's not connected to the Andes. Then the river, although there's evidence that it has moved around, there's not a visual sense that it's moving around very quickly, or there's a lot of activity. So that led to, and the same thing with the, you notice here, the bars are very limited in extent. And there's not much activity, not fresh activity in the floodplain. It's old activity, but not fresh activity. That led to the hypothesis. Oh, by the way, that's a picture of just what I'm talking about with activity in the floodplain. Right? You just see the complexity of these floodplains when the river's moving around a lot. And ecologically, this is tremendously important to the biologists. I mean, these lakes are teeming with life. River dolphins, big fish, delicious tasting, really, this scale fish. And this is, one of the Garden of Eden of biodiversity in the Amazon is in what geologists would call the Fallen Basin. It's not the central Amazon basin, it's the Fallen Basin. It has the greatest biodiversity. This is a clearer picture on the ground of one of these optical lakes. They're just teeming with life. You get a little boat in there, there's fish around all over. So it led to the hypothesis, this spatial association I said, that sediment supply, I won't go into the details of data processing, but sediment supply influences the rate of channel migration, the frequency of channel cutoffs, of vulsions, and maybe even the rate and the style of meander deformation. In other words, are the bends growing by extension? The river's traveling that way. Is most of the action like this way? And the meanders are mainly extending? Or are they translating downstream or upstream? Okay? So that's what I mean by these three hypotheses. And we tried to test them, but unfortunately you can't, since that hypothesis is about sediment supply being the driver. Well, there are very few places where we can measure or obtain data on the sediment supply. So that limited, the range of sampling I could do in the basin, or we could do in the basin. But anyway, finally, with one of my former grad students, Jose Constantine, and one of his graduate students, Joshua Ahmed, we got these sediment supply rates, and then we were able, we noticed, by the way, that some of them are in the Andes, this green area here, so we expect the sediment supply rate to be high here. Some are on the craton, we expect the sediment supply rate to be low, and some in the middle, in the tertiary lacustrine sediment geology, we expect to have intermediate sediment yields for this, and that's true. So that's basically the thing we're sampling. Now, then we have about 40 years of evidence of channel change in the Andes, in the Amazon, because so we can go and overlay digitally channel courses, so with this we can measure the rate and the style of meander bend deformation. And this eventually became the PhD thesis of this man, Joshua Ahmed, who's the graduate student of my former grad student. So the three of us are working together on this. And I don't, because Joshua has not yet published his own PhD research. I don't want to expose him publicly, but I can tell you generally what he found out. But this one is published. So, you know, we test this hypothesis that sediment supply appears to be the driver of channel migration rate and cutoff frequency. This is the data set we got. Now, you know, there's a lot of scatter here. These are, you know, logarithmic scales, but there is a measurable positive correlation between. So the higher the sediment supply, the higher the channel migration rate. The higher the sediment supply, the greater is the frequency of channel cutoffs. Okay. Now let me say, although these are just statistical associations, in a river in Central California, I spent 10 years doing detailed measurements of how sediment supply affects these two processes, bend, erosion, and bar growth, create the channel migration rate, and the cutoff frequency. So I have a mechanistic basis. It's not just like, oh my goodness, I've got this geographical association. It's simply to say, okay, given this mechanistic understanding I have from California about why you'd expect that association, if I look at the whole Amazon basin, I can still see a signal. So that's my approach to this. Now, let's see, the number of oxbow lakes in the floodplain are created by these channel migration and cutoff processes is also correlated with the sediment supply rate. So what the thing I don't have data to show is Joshua's latest result, which is that the higher the sediment supply, the greater is the bend deformation. That's sort of a downstream deformation of the bend. In other words, the bend starts out like this, like a sine wave. It will grow that way if the sediment supply is high. It will extend if the sediment supply is medium, and it will migrate upstream if the sediment supply is really low. Basically, that's So here then is an environmental implication of that. So what we've established here is there's a lot of activity between exchange of sediment between channels and floodplains, responsible for forming the complexity of the geomorphology of the Amazon floodplain, where those sediment exchange processes are very high. There's a lot of complexity. Where the river is constrained tectonically, there's not much exchange, then the floodplain is not very complicated. And established also that if the sediment supply coming down from the tributaries is high, there'll be a lot of activity. If it's low, there'll be small activity. That means that if you did something that shut the sediment supply down, should you expect strong environmental implication for that? Well, of course, here is a map of planned hydroelectric reservoirs, dams, that shut off the sediment supply coming from the Andes. And so here's a field site. This is on the Beni River, where the river comes through a notch out of the Andes, and it's carrying 250 million tons of sediment every year. And that 250 million tons is supporting the complexity of the wetlands that I showed you pictures of. Right? The hydrologists and the biologists think that what's supporting the wetland, creating the wetland, is the water. And the water's not going to be reduced by hydroelectric. But I'm saying, no. What's creating the diversity and everything you value is the sediment. And you're going to shut it off. And it will go to zero. These proposed, these are intermontane trenches. Or you close off that site at a place like that, right? Which is that site I showed you. With a very small, narrow but high dam, and the upstream intermontane trench is vast, so no sediment is going to come out of it. Okay? You're going to shut this sediment supply off. This is another tributary, Marañón. This is a site that's proposed to be dammed first. So, this is this is threatened by this shutting off the sediment supply. So I asked, well, what's our evidence? What do we know about this when it's happened elsewhere? Here's the result for when Glen Canyon Dam went in on the Colorado. Downstream, the river declined 3+ meters. The bed of the river was degraded 3+ meters. So I said, well, if that happens in this particular case, what are the environmental implications? So, yes, it's a very crude, simple quantitative model to try to just get the point across. Here are satellite-based maps from one of my colleagues, John Milak, of the extent of wetlands in the Folded Basin. And the area at any one time, the flooded area, is correlated with the stage of the river. Like the rivers that drain, the major rivers are the drain for this wetland. And we talk, you can't see the scale here, that's 80,000 square kilometers. When the river's up at its highest stage in a wet year. So I constructed a little, geomorphological, hydrological model here. So if we have X discharge and it's going into a channel as big as, take a representative channel cross section and floodplain, how high will the river be today? If we then put the same discharge down through the same channel, except we've lowered the bed here, what difference will that make to the elevation of the water surface that's providing the basis, the base level, if you like, for the wetlands? So, I won't go through all the details of how I did this, but this is for different degrees of incision, whether we have 3 meters, 2 meters, 1 meter of incision. But basically, the answer is this, that if, for example, we have a lowering of this water level as a result of bed degradation by this amount, then it will lower the drainage area, it will lower the area of the wetlands by that amount. And the same thing to do this over here. And the answer is that the likely implication of this bed degradation produced by shutting off the sediment supply is thousands and thousands of square kilometers reduction of these beautiful organized wetlands. And they're all supported by the sediment and the channel activity, not just by the water. So I will stop there. Just one example of the environmental implications of this recognition of the fact that the sediment supply is the major supporter for all the wonderful activity and complexity of these floodplain environments. I'll stop there. Thanks.
One important question. Okay. Okay. I will push our Israeli colleagues to more concise time. Otherwise, we will not